we have a scheduled break today at 10:30. So I'll try to give you all this information just like all together. And I hope that at the end of the class you will be convinced that if we can observe with ALMA and get any signal from the sky, it's just because Pachamama is it's a miracle of Pachamama. Okay. Today I am trying to explain you all the effects that we need to correct for in able to get to the point in which we can start imaging. So this is about all the steps in between have been done by somebody or by the pipeline in order to correct the data sets so you can image them. It's not like a straightforward thing, and indeed, even for me, it's quite technical because I don't, it's a lot about engineering of the antennas, of the receivers. But I hope, I mean, you're a physicist, you know much better about circuits and all these things, right? So I'm sure you, if you have questions, please ask, because perhaps I can explain already, but it's a bit of a general idea, because in principle, you will not need to do that yourself. But it's good to know all the corrections that have been applied, because when you go and look into your UV plots, and you see like some strange points dancing there, you may know where are they coming from? Are they coming from a bad antenna? Are they coming from a bad correction of the water vapor? Are they coming from? So you need to know a bit all the steps that we have been performing. Here I just put you some reference of documentation about this step about calibration. And I wanted to mention that I made use mainly of George Hill's slides in the last European Radio Interferometry School, which are I think they are very nice and very easy to follow. So very briefly, I wanted to put this slide again because we were talking about the correction of the primary beam. So I showed you that this is an antenna, and then you have like the response. And the response, you have like a very good response towards in the straight line, but then you have secondary side lobes where some radiation can come in, like ambient temperature. You can have contamination here. And this is to show you the primary beam of an ALMA antenna. This is what we have been putting in the formulas, right? So this is the response of an ALMA antenna of 12 meters. This is the angular offset with respect to the center. So you can see here that you have very good response in that direction, but as soon as you start moving apart, you have nulls, and then you have secondary side lobes. That's why we correct our images for this pattern, and this is what we need to do if we want to make a measurement of the flux from the source. We need to correct for that. If you just want to have pretty images, you don't need to apply the primary beam correction. It's when you need to make flux measurements that you need to do that. Okay? So you have, I have shown you here like one of the things that we need to correct when we are thinking on the antennas, but there are many other considerations that we need to take. It's not so easy. So the antennas have surface errors. They need to really like correct for any surface differences that there are in the antenna. There is also, for instance, parallactic errors. Depending on the mount of the antenna, you might have the azimuth mounts like ALMA antennas. That creates also an error in the parallactic angle of sources, because as long as the time goes by, the sky rotates on top of the sky that sees the antenna is rotating. So then you have a change in the parallactic angle. This is a small disturbance, but you need to correct for that. You have pointing errors, depending on the location of the antennas. You need to correct for that. You have elevation effects. The antenna does not respond the same when it's down than when it's up. You have then instrumental polarizations, so the receivers and the way the optical configuration is set. If you have like the feed here, if you have the optical in another location, depending on the path that the electrons need to follow, you may end up having detecting a polarization from a non-polarized source, and this polarization is just coming from the receivers. So all these effects need to be corrected for. This is quite technical and very complicated, but it's already, so you are aware that all these steps are there and being applied. And every one of these corrections is putting some much more uncertainty or correcting it for the good. You never know. Just to show you here, how do the receivers look like? For me, like, the antennas are a black box. They are inside there. There are like some receivers. Well, this is how do they look like. And actually, they are in a cryostat. So they are all in a very low temperature system to avoid, to have good response from the receivers. And so this leads us to the point on why do we need to calibrate, right? If ARMA is so perfect, we know the antenna so well, it's not so perfect, and then we need to correct for all these effects by using some knowledge that we have from sources in the sky mainly, or from the instrument itself. So many tests, many simulations, in order to sorry?
Many tests on things we know pretty well.
Yes. That's how we are going to correct for these uncertainties, for these effects. So for instance, we will be observing sources that we know that are bright, that they are point source-like, in order to correct amplitudes and phases. We will be using, because we know the response of the receivers, we will be injecting artificial temperatures and see how is the receiver responding. And then we will compare to the response from the sky. And then we will, with this way, we will measure the system temperature, the noise of the system. So this kind of tricks is what we do in the calibration process. Yeah, so this is a schematic view again of, we had the ideal case, and we were observing the wave coming, we had the delays. Well, now the delays are affected by extra things. The atmosphere is causing some disturbance in the signal that we receive. The positions of the antennas, if they are not perfectly correct, you also have uncertainties. Every receiver may respond differently, so the amplitudes may be different in between antennas, right? So all this, we need to correct for all of this. Okay, these are like the same factors that are appearing more or less here in this schema. So you have, as I said, disturbances from the atmosphere. You have errors that come from the antenna itself. You may have errors that come from the correlator. So all that signal that goes into a correlator, you may have also errors in that part. If the antennas are not fully synchronized with a common clock, you need to really measure the time pretty well. So that's also another source of uncertainty. Like for LOFAR, for instance, the central part of the array, they are all connected to the same clock. So exact clock, all of them have the same clock. But the outer antennas, they are far away. They have their own clock systems. When they combine the data of the core stations with respect to the remote stations, they need to correct for the delays in the clocks of the remote stations. Okay? This is just, an example of all the factors that can affect the signal that you want to detect. Also, also not to mention, if we are willing to detect a line and we are observing in a certain bandwidth, the response might not be the same. It may not be uniform. You may your response might be better in one part of in one frequency range than in the other, okay? So we will need to calibrate the bandpass as well. So all of this, you can try to simplify all these factors and express this as, okay, the visibilities that we are observing are the true visibilities corrupted by certain factors, okay? And then you try to split all these factors in steps. So every step that is affecting your visibilities, you try to correct for it and apply the correction, and then the next one. Okay, solving this equation is what we call the measurement equation. So we need to find these corrections. And for finding these corrections is when we use the sources that we know well. Then we find the factors and we apply those factors. And then we can go to the source and start working with the visibilities. Okay, here, as you can see already, the factors have been like divided in several steps. So this is the true sky visibilities that I would like to measure. And this is the one that I'm observing. So here you have like parallactic errors, gain, like phase and amplitude errors, bandpass errors, temperature, the temperature of the system. So, okay, you need to solve for every one of these factors here. Yeah, we are assuming there are several ways to approach this problem. We are assuming that all these factors are antenna-based, so for every antenna. You could think of these factors baseline-based, and you would use kind of equivalent equations, but trying to solve per baseline instead of per antenna. We are using like an antenna-based because the solutions are much easier to, I mean, the problem, the numerical problem is much more, is confined. And the extra baseline effects, you can try to add them as also antenna-based. Okay, so what we do, we do a primary calibration. Yeah, tell me.
If you were to measure from the outer space, all those factors would be one. I mean, the visibility would be the true visibility.
If our interferometer was in space, like in a satellite flying, no. You will still have all the instrumental effects from your receivers, right? So if your receivers like have thermal noise because they are not perfectly at, I mean, there is some noise always there. So of course you would avoid the atmospheric effects, but you may have other effects up there instead, right? So you would avoid the atmospheric ones, but the ones that are related to your receivers, you will still have to correct for them. And that's what they do when they build a satellite. Before they launch it, they try to simulate everything that can happen to that satellite, to calibrate that. And then when they launch it, they hope it works.
So it is not so worth to put that satellite with an antenna receiver in space.
It's not so much work.
So worth.
So worth. Yeah, well, there are projects to, yeah, why not? Depending on the wavelength that you want to observe, right? So there are projects to make a small interferometer in space with several antennas, like.
For example, for bands 7, 8, 9.
Yeah, okay, I see what you mean. But then you need the resolution. The good thing of AMA is that we can expand the array 15 kilometers. If you are willing to make like a Death Star there of 15 kilometers of, you know what I mean? A system of 15 kilometer antennas in orbit, right? Yeah, it's a good point. So you can go outside the atmosphere to try to see something in those bands, but then you need the resolution as well. Okay, so we first do a primary calibration, which is in order to try to get rid of the effects that are time independent. Okay, and then because I will be observing my source for a longer time, I will make stops every now and then to try to correct for time-dependent effects. Okay, and finally, one final trick that you can do if your source is strong enough is try to self-calibrate. This is really a bit of a magic thing. So self-calibration, you will see it a bit later, is to use a model of the source to try to correct the visibilities that you have so they fit the model. And you make some iterations, and in every iteration you make a new image, extract a new model, and try to self-calibrate again. I will explain that later, but basically there are these 3 steps. This is an example on how is it implemented in CASA. So you can actually try to add all these corrections. This would be the true visibility. First, we look for the opacity in the atmosphere, errors due to elevation, amplitude and phase, polarization, instrumental polarization, bandpass response. So you observe a bandpass calibrator that you know has a flat response. It has no like lines in the bandwidth that you are interested in. You observe that calibrator, and then you scale your response to that calibrator. So then you have a flat bandpass. Okay, and then other baseline effects. So finally, in order to try to go back and get the true visibilities. Those will be like the ones that go into the imaging, okay? And then you have already seen all the problems that you have. Okay, so first, I will just explain very briefly what are the atmospheric effects for ALMA. So this slide is just to show you that the main effect for ALMA is the water vapor. This is a 10-kilometer height. So ALMA, which is around here, you have basically the H2O water, which is causing opacity. And also, this is not constant because you have clouds, it's turbulent. So you need to track the atmosphere every now and then, as much as possible in the case of ALMA. Yeah, so this is also to show you a comparison of the VLA site, which I think is around 2,000 meters in New Mexico, and then the ALMA site. At those frequencies, in the VLA site, you can see nothing. Whereas at 5,000, the atmosphere allows you to see. It's not so opaque. But this profile is not always the same. It also depends in time and depending on the conditions. And in the next slide, here, you can see that not only you have H2 water, but you also have oxygen lines and etc., other components. And here is to show you that this opacity is not constant. It also depends on the amount of water vapor that we have at that time. And if you have like very dry conditions, you are able to observe in the highest bands of ALMA, in the highest frequencies. Whereas if you already have, you can see how it affects the response. So the opacity of the atmosphere when you have a bit more of water. And for that reason, they are always monitoring the PWV. And depending on that value, they decide mainly to observe in the lower bands of ALMA. If you have higher than 1 millimeter, you are safe to observe here. In those bands, you really don't want to go until you have very dry conditions. Okay. So how do we correct for the atmosphere? Well, we model it, basically. So we treat it as a it creates an attenuation in your source, and it also has its own temperature. So it's also it's adding you an extra temperature on the sky temperature that you are willing to measure. Okay, and also it depends on the elevation. So you will need to correct for that as long as your observations go. Okay, so here it's a way to express how are we going to correct for the atmosphere opacity. In principle, we are observing the sky, and we have our source and the cosmic microwave background. This is what we want. But on top of that, okay, it's attenuated by the atmosphere. It depends on the elevation. And on top of that, we have the noise from the atmosphere itself. Okay? And well, here in this case, the formulas are much more complicated. You can carry this all along, and you will get like a super long formula. But to simplify, you can kind of forget about the CMB because it's only 3K. You can add the contribution of the CMB to the atmosphere component or whatever you want. But basically, you end up having the temperature coming from your source attenuated by according to the elevation, the atmosphere noise, and the receiver noise. Okay? And we want to get rid of that. This, okay, so if we divide this over this, we want to get rid of that. Okay? And this is what we call the system temperature. For ALMA, they figure out a way in order to measure this, and then we divide the visibilities that we are observing by this factor. Okay? So there is a constant monitorization of the system temperature of ALMA, of the antennas. And we divide for that. So the system temperature is a time-dependent measurement of the sensitivity of each antenna. We are trying to measure all the time this contribution here. Okay? So it takes into account the atmosphere noise and attenuation and the receiver noise. Technically, it's much more complicated, okay? But what they do basically is to load two different temperatures to the receivers at 20 degrees and at 80 degrees. They go changing, and then they observe the sky. And yeah, by making like simple computations, then you obtain what are the contributions of the atmosphere and the receivers. And then you can subtract that contribution. It's a bit more, it's complicated, but the trick is to use two different temperatures, which is something I think quite new for ALMA, because usually they manage to put only one. And by using two, you manage to disentangle both of them. Okay, and how does this look like? So this is the response, the system temperature of the antennas during an ALMA observation. Okay, and then you can see like the contribution of the PWV here. This is in frequency. So you are monitoring all the time, monitoring in time and in frequency, depending on the observations you want to do, the response of the antennas. Of course, yeah, this correction might be good or bad. If the antennas are very noisy and you divide by that factor, what happens? Your visibilities go up like crazy. So you want to make, you want to make sure or the pipeline will checks these results in order to flag antennas. If an antenna is very bad, it's behaving very widely, you drop it out, because it's going to add you a lot of noise and the amplitudes will be very, very high. Okay, and this is an example to show you how the raw visibilities would look like as time goes by, because the elevation of the source is changing. But because we have the information of the system temperature that includes elevation effects, then when we correct, we have like kind of constant amplitudes along our observing time. Okay? So when you make an image, you are not using visibilities that are affected by elevation as the time goes by. Okay? Excellent. What time is it? Okay, so we have half an hour. Excellent. Okay, so how does it look like in reality when we observe with ALMA? How often do we need to make these corrections? How do we do? Okay, this is a classic, well, just one example is a typical ALMA observation. Our science target is this here. This is the observing time of my source, the one that I'm really interested in. But then I need to perform several other observations to correct for all the effects that we were talking about. So we will start like with a pointing correction. We will measure a source that we know the position with, and then we correct the pointing of the antennas, for instance. We measure the atmosphere. This is the load that we were talking about several times, okay? The bandpass, as I said, the response of the receivers is not uniform in frequency. You may have like much more sensitivity at certain frequencies than others. So you observe a calibrator which is strong, and then you divide your response by the bandpass of the calibrator. Then we have an amplitude calibrator. Then we have, in between our source, we have a phase calibrator every now and then, okay? And you can see here something in green, which is happening almost all the time. This is the water vapor radiometer. Because ALMA is so sensitive to the effects in phase that the atmosphere creates, you need to monitor it a lot. We will talk about that now. So basically, yeah, after all, you are observing for a certain time, but quite a fraction goes into calibration, into observing other sources that are not your target, okay? Okay, why do we care about the water vapor? Because when the electrons go through the atmosphere, they are diffracted. So they start like bounding, and then when they get to us, they have suffered a change in phase. And in the case of the wavelengths at which ALMA operates, these shifts can be quite significant. Okay? Remember that it's like a blurring of your image. If you are trying to take a picture with your phone and you make like this, you will get something blurred. It's not well focused. And yeah, I wanted to say something else. So yeah, basically that the effects of the wavelengths that ALMA is observing are quite important. Yeah, remember that we know from the UV plane that a point source should look like, when we look to the Fourier transform, should have constant amplitudes and zero phases, right? So what we can do to correct for the phases is to observe every now and then a point source and try to make the phases zero and the amplitudes constant. But on top of that, even when we are observing such a source, we are having the noise, the phase changes from the atmosphere itself. So what do? Okay, they model the layer of water vapor as a single layer that is causing, it's a screen, and it's causing a delay in the signal that goes through the atmosphere. And what they do, actually, well, this is just to give you a measure. So at 300 microns and at 0.3 millimeters, a small path error of 25 microns, just because of the water vapor that is there, would imply a phase error of 30 degrees. This is huge. So in your plot amplitude, in your UV versus phase plot, you will have like a noise of 30 degrees. That you don't want that. So what they do is they have put water vapor radiometers at every antenna, and then they observe a very strong water line that we have at 183 gigahertz, and they look for the fluctuations of this line. This is a very strong line. So if we see changes on the response to that line, then we can estimate how much water vapor was there. Okay? So that's how they do that. They use, the atmosphere is our worst enemy, but in this case is our source for making a correction. We make use of a very well-known defined line that it's blocking our, it's causing an opacity. We measure that, and we measure the changes with a radiometer, and that's the correction that we are going to apply. Okay, so again, all this here is just to measure the phase variations from the water vapor. Okay? So you can see that this correction is not applied for other telescopes that are not affected so much. Okay? Again, so we have all these different components. So now we will take a look to the errors that come from gain and amplitude from the receivers itself. Sorry. Yeah.
I don't understand what is the difference between pointing and phase.
It's related. Yeah. So, well, when you have phase errors, it's much more difficult to say where a point source is located. But pointing errors, from the antenna point of view, is that you expect that, you are pointing towards a direction, but what ends up coming in at the end is not exactly that. But it might be slightly changed because your focus is not perfect, right? Depending on the antenna itself and the receivers and how is the transmission done, your pointing is not what you are. You are pointing there, but you are getting something slightly different. You don't have a perfect lens.
So pointing is a problem of
Location of
the antenna itself, and phases because of weather, or no?
Yeah, phases. So you have pointing errors from the antenna itself. Okay, assuming that you are just observing a thermal object not far away, you will have pointing errors, right? Because the antenna is not perfect. If you have like a lens that is not perfectly collimated, then you will have pointing errors. This is the same, okay? What the atmosphere does is adding much more phase noise. So if you are trying to correct, for instance, for these pointing errors by using a source that is in the sky, let's say that with other instruments, we know the astrometry of a certain source, and we point to it with ALMA, and then we try to correct for those pointing errors by using that. But then in between, we have the atmosphere that is causing extra noise. So making the astrometry is going to be complicated because of those issues. Okay. So at this point, I'm sure you are convinced that it's impossible to observe with ALMA all these corrections that come from nowhere. Okay, this is the diagram that I like a lot. So assume that we have already managed to figure out to correct for the water vapor, etc. We still have some other uncertainties, like the amplitude at every antenna, and the bandpass, for instance. So we first observe, for a short time, a very bright calibrator. We call the flux calibrator, and with that we solve for the amplitude response of the array. Okay. And then, of course, I want to observe this target, but if I move from here to there, I have already changed. There are many changes, like the atmosphere is not like the same at here, the variant than here. You have other contributions as soon as you change the part of the sky that you are looking at. And you also want to measure short changes. You want to control that. So what you do is you observe a phase and amplitude calibrator here as well, which perhaps is not as strong. Unfortunately, there are not many super strong sources in the sky. So then we look for another not so bright, but is much closer. So we can assume that the sky behaves the same in between my secondary calibrator and my target. Okay, and ideally, like we go on a point source that is close enough to your target. So then we do first short observations of a very bright source. We need it short because it will give us a very high signal to noise with a short observation. And we correct for flags, bandpass, etc. Then we go to a secondary calibrator and we calibrate amplitudes and phases. And then we observe the targets. And then we apply the solutions first from here to here, and then from here to my target. In principle, my target is an unknown field. It's something that I don't know yet. I don't know if it's a disk, if it's a point source, if there's anything there. So unless I'm already observing something that has been observed before, I don't know how it behaves. That's why I'm using a point source-like source that I know to get all those corrections. Okay, this is just to show you this first part here, the flux calibrator. So you want to observe a strong source. And because you have many baselines, at the end you can find a solution of your measurement equation here, okay? Like the gains, the amplitude and phases. Okay, and this is to show you an example of a source that if you observe it, you want to use it as a flux calibrator, but you observe with too much resolution, it's not a point source anymore. And then you need to start taking into account the structure. You need to model it. This also happens for ALMA because we use planets as calibrators. So we need to have a good model of the planets in order to use it as a flux calibrator. So it's really a field I mean, it's investigation ongoing because still the models of the solar system objects are not perfect and are not perfect either for the ALMA band. So there is a lot of work in order to improve those models for calibrating better our observations. So not everything is done. You can still come to work with ALMA and solve issues. Okay, in principle, you also need to know the spectrum of that source. If you are observing in a wideband, you may have, right, different intensity with frequency. So you may want to know the spectrum of the source. It's not as easy as taking just a flat, constant amplitude source in that frequency range. This is an example of typical calibrators that are used, that they are the strongest radio sources in the sky. So if you, as George and Skype did, you need to observe them at several frequencies in order to get a good model of their frequency, of their behavior with frequency. Okay? And this is an example on how would be an amplitude correction, how the calibration would be done. So we will have like the raw amplitudes here of our calibrator. Remember that if we assume it's a point source, all the amplitudes should be constant. Okay, so we find a solution we find all those factors in the equation that I showed you before that make these amplitudes flat. Of course, yeah, it's very difficult to make them all completely flat, right? But at least they look like, okay? I have managed to constrain the flatness of the source. So by observing a calibrator and obtaining these solutions, I'm calibrating the amplitudes. Okay? Then I have a phase calibrator. So I observe a source which is nearby my target of interest. And with that calibrator, I managed to correct for residual phase differences in the field of view. Okay? The same exercise that I have done for the amplitude calibrator, now I do it with the phases. So I look for an ideal point source-like source, which is nearby my target, and then I apply the solutions to my source, because in principle, the structure of the source that I'm willing to observe, I don't know it yet, right? Okay, if you want to look to how all these steps are implemented in CASA, you can just go to one of the one of the targets that we have been taking a look into it, TW Hydra. If you go to the CASA guide, the part that explains step by step how the calibration is done, you can perform all these steps one by one, but you can see all the commands in CASA. But it's basically written in Python-like language to apply all these corrections. System temperature, water vapor, radiometer correction, amplitude correction, phase correction, etc. As I already said, so in 2 weeks is not a lot of time, but you just need to be aware on the complexity of the system. You don't need to perform all these steps yourself. Somebody else will do that for you if you get ALMA time, or the pipeline will do that. Okay? What time is it? Okay, excellent. I think in 10 minutes. So after doing all this process of calculating corrections by observing known sources, if after all I go to my target field and I image my target field and still it doesn't look right, it's very noisy, it's like, I can do one final strategy, which is called self-calibration. It's a bit of a tricky thing, but you basically try to use a model of your source in order to obtain the correction to residual effects that you might still have. And how do we do? Our source is unknown. It's not a point source. It's not, unless you are observing a calibrator, which can happen. This is my job, observing calibrators, by the way. For me, it's very easy because I observe a source and it's a point source. So I only need to calibrate the amplitudes, put them constant, and put the phases to 0. But as you have seen already, if you have a disk or if you have like a ring or something else, it's not so easy to calibrate in the UV plane. So we need a first model. What do we use as a first model? Okay, we make a first image, and the model that we get from that image, the cleaning components, we use them as a model to calibrate the residual phases and amplitudes. Sounds a bit weird, right? Because I'm using, if my model is wrong, right? Well, if your model is very, very wrong, if you have not been cleaning well and you add fake sources that are not real in your model, your corrections will not be good. It will make the image worse. But in principle, if you start with a very simple model, let's say that you have a disk. So you make a very short cleaning with the basic structure of a disk, and then you use it for doing a first calibration step. You calculate solutions for phases, And then you apply those solutions and make another image and see how it looks like. Okay? Then you can change the time in which you are calculating solutions. You might decide to, when you look at the solutions, you might decide to choose shorter times. Perhaps with 1 point for all the observations, you have enough. But you may want to make shorter times to calculate a new solution. You make a new image, and you feed it again. So you make this cycle until you don't obtain much better results by applying a new calibration. This is what is called self-calibration. You are calibrating the object with itself. It's a bit of a redundancy, but if your input model is okay, then you are getting rid of extra phase noise and extra amplitude effects. Okay. Yeah, and this is basically to finalize the full loop. So if only my target is bright enough, I can do that. If your target is not bright enough, as we had with the disk, you cannot make self-calibration because you will not find good solutions. You will not have enough signal to noise to get the corrections. Okay? And then when you apply those corrections, your image will be even worse, basically. Okay, and this is an example of self-calibration with LOFAR. So this is the Perseus cluster. I think you can see it much better in your screen. This is before self-calibration, and this is after self-calibration. So several iterations have been applied here. Every time you make a new image, you solve for the calibration solutions, you apply them, you make a new image, until your improvement is kind of negligible. And then, look, so you manage to get rid of residual effects, mainly phase effects in your field. Okay, so yeah, and this, I think this slide is just to mention that it's in self-calibration, it's very important to choose a right interval of time in order to calculate solutions. Yeah, basically that's it. After the break, we may take a look to one self-calibration example. This is the data that I have put in my website that I have just sent you the link to my webpage. Have you downloaded the data? Okay. It's okay, we can do it later. Yeah, so I think we have a break. And if you can download the data already. Yeah, we have to correct the test. Sorry. Yeah, I'm going to put the break thingy, but. So yeah, here you can find the link to the data set. I also have a pen drive if you guys have problems to download. Okay, I think. Okay, this is the test that we did today, right? Oh, I forgot one question. What is?